Okay, so let's get started on our next lecture. So we're on the lecture 5 now, force vibration. Okay, so what we're going to do is we're going to do something very similar to the free vibration that we just done in the last couple of lectures. Okay, so we're going to go through the undamped forced case first and then the damped force case and derive the equations of motion. Okay, so we're going to start with undamped force vibration. And so what we're considering is a system like this, mass spring damper. Okay, so where all of our notation is the same as before. So we've got a mass M sitting on the spring K, okay, but this time we've got something shaking it, okay? So we've got some additional force, which I'm going to call F of T, okay, which is shaking the mass up and down in some way, okay, and our displacement X is still just constrained to be in the vertical direction, okay? So, and this of course is the undamped problem because there's no damping element, there's no dashport or anything, okay, so just a spring to give a restoring force. Okay, so we want to derive the equation of motion for this, and we're going to do that by drawing the free body diagram. Okay, so what we do is we take the free body diagram of the mass, and if you remember we did this before, so if for example we assume that the mass is pulled up slightly, okay, from its original position, then what happens is there's an inertia force which is trying to resist that, which is mx double dot. There's also a spring force which is trying to resist it, which is k times x. But there's also this additional force F of t in this case, which is acting on the mass. Okay, and the way I've drawn that in the diagram is that at the moment that's acting upwards, so we'll do the same for the free body diagram. Okay, so that's our free body diagram for our mass. And so from that, our equation of motion, so EOM is just short for equation of motion. So if we take a balance of the forces in the vertical direction, we can write the equation of motion like this. So this is exactly the same as the equation we derived last time for undamped vibrations, except on the right-hand side we've now got this F of T. And if you remember in the lectures previously, I put that to 0, and I said there's a convention that we put the forcing, external forcing terms on the right-hand side of the equation. Okay, so now we've got one of those terms, and it's there, it's F of T. Okay, so we're going to take a similar approach to what we did before. We're going to assume that there's a harmonic forcing, a harmonic solution and a harmonic forcing. Okay, so we're going to do the forcing first. Okay, so what does that look like? So if we assume a harmonic forcing, what we're doing is we're taking for now that F of T is equal to some constant F times e to the j omega t, okay, where we're using the exponential again as a way of introducing sine waves, aren't we? Okay, just like we did in the previous. So this is the shaking or the forcing of the mass, okay. And we're also going to assume a harmonic response. Okay, so x of t is now going to be assumed to be some constant, which I'm going to call xa, e to the j omega t minus phi. And I'm going to explain what these different terms are as we develop this idea. Okay, so there's a couple of things to note about this which are different from before. Okay, so the first thing to note, so first of all, note that omega is not the natural frequency. Okay, so in this, what I've written down here, omega doesn't have any subscripts. It doesn't have an n, it doesn't have a d, which it previously, when we found the solutions for the unforced case, we found these natural or damped frequencies, didn't we? Okay, so this time, it's omega without any subscripts, and that means it's what we call the forcing frequency. So omega is the forcing frequency. So what does that mean in terms of the physics? Well, what it means is if you take a system like this and you shake it with a sine wave, it tends to respond at the same frequency you're shaking it at, okay? Whereas previously, what happened was it responded at the natural frequency or the damped natural frequency, okay? So if you think about it, if you have a system and you release it from an initial point and you're not forcing it, all it can do is oscillate at its natural frequency. Okay, whereas if you're shaking it deliberately with a particular frequency, then it tends to respond at that frequency. Okay, so that's why the forcing is at omega and the response has got omega in it as well. Okay, so that's the first thing to notice. The second thing to notice is that the response has got this extra bit in the exponential, hasn't it? Which it didn't have last time. So it's got this thing phi. Okay. So we did talk about phi a little bit last time. Phi in the context of forcing, okay, is there to represent the delay, or sometimes it's called the phase lag, between the shaking signal, the forcing signal, and the response. Okay? So note also, so all that means is if we have a time graph and we start shaking something with f, so this is f of t, then it starts to respond at a slightly delayed time, which is x of t, okay? It means if you start shaking something, it takes a little bit of time for it to kind of respond, okay? Usually, that's what normally happens. So there's this sort of delay or lag between when you start shaking it and the actual shaking signal and the response, okay? And so we represent that with this thing phi. So what we're going to do is exactly what we did in previous times is we take these expressions with exponentials in and we substitute in the equation of motion. So we sub for f of t and x of t in EOM, equation of motion. And we'll also use the fact that in this case x double dot is equal to minus omega squared x. Okay, so if we look at the assumed solution for x and differentiate it twice, each time we get a j omega. Okay, so j omega squared is minus omega squared. So if we do that, let's see what happens. So if we substitute into the equation of motion, what we get is this. We get minus omega squared m plus k, and then there's a bracket xa e to the j omega t minus phi. That's all on the left-hand side of the equation, and on the right-hand side we get f e to the j omega t. So what we want to do is we want to try and get rid of the e to the j omega t's on both sides here. Okay, so we can divide this exponential up into the multiple of e to the j omega t times e to the minus j phi, can't we? Okay, and what we're going to do is we're going to define a new variable, or let's say setting capital X equal to xa e to the minus j phi. Okay, we can take the e to the minus j phi into this sort of new kind of constant called x, if you like. Okay, so if we do that, then what we'll have is minus omega squared m plus k in the bracket, and then we have x e to the j omega t equals f e to the j omega t. Okay, so that's just we're going to come back to this phi term in a minute. Okay, but that's just to show you how we can divide that exponential up, and then essentially we can divide out the e to the j omega t terms from both sides. So that means that we can write x over f is equal to 1 over minus omega squared m plus k. And for forced vibration, these kind of expressions, we're going to derive expressions very similar to this throughout. This is like the ratio of the output to the input and what it is on the right-hand side. Yeah, sorry, do you have a question? Why did I? It's because just like in the undamped case, the assumed solution is this. Okay, so if I differentiate twice, I get a minus omega squared out the front times the original thing. So x double dot is equal to minus omega squared x. Is that okay? So let's go back and deal with this issue of the e to the minus j phi. Okay, so we know that x contains this term e to the minus j times phi, and that's a complex exponential, isn't it? So in general, it's a function like this, e to the j phi, and there's some angle here, and these are sort of real and imaginary, aren't they? So this is like a complex exponential on the unit circle, isn't it? So if we want the things to be real, we have two options, don't we? Either the angle is 0 or it's 180 degrees. Okay, and that means that we're choosing these 2 points here, aren't we? So for x to be real, phi is either 0 or pi. And so that means we're restricting this term, e to the minus j omega, to be plus or minus 1, aren't we? Okay? So e to the minus phi is equal to plus or minus 1. Okay, which is so that this is a complex exponential on the unit circle. So if we choose 0 or pi, we have to have plus or minus 1. So we're going to bring this together with another typical convention is we're going to use the static force relationship. So if you remember back to when we talked about the static force relationship, that's equal to the force over the stiffness, isn't it? Okay, so if we think about our assumed solution for the force, in the case when there's no dynamic motion, so when time goes to 0, okay, the e to the something t term goes to 1, so we're left with just F. Okay, so that's just what we would call the static force, if you like. You can think of this as the force at 0 frequency or 0 time. Okay, and so in that case the mass would deflect by this amount, wouldn't it? If you apply just a static force with no dynamics, it's just related to the stiffness of the spring. So then what we're going to do is we're going to write our dynamic displacement, which is x divided by x static, like this. So that's equal to x F over k okay. And we also want to note that our expression x over f can be written as, well, what we've got at the moment is k minus omega squared m, haven't we? But we can actually write that as 1 over k, 1 over 1 minus r squared, where r equals the forcing frequency omega over the natural frequency omega n. So if you see what I've done here, I've got this expression and I've taken k outside this bottom term, so I've got k times 1, I've got k being taken out of this term here, which means I have to have m over k here to correct that term. And of course m over k is 1 over omega n squared, the natural frequency. So I've got omega squared over omega n squared in this term, and that's equal to this new thing called r, or r squared. Okay, so r is the ratio of the forcing frequency to the natural frequency. Okay, so I've got my x over f like this. So then if I combine that with the line above, where I've got x over x static is x over f times k, then I get rid of this k, I get rid of the 1 over k, so I end up with x over x static is just equal to 1 over 1 minus r squared. Oops, sorry, that should be just 1 there. Okay, so that's 1 minus r squared. Sorry about that. That looks like r minus r squared, which it shouldn't be. Okay, so that's 1. So this is our first kind of important result for forced vibration systems. This is called the dynamic magnification factor. Okay, so sometimes this top term x is sometimes called x dynamic. So it sometimes has a subscript dynamic or dyn. So what it's saying is this is the ratio of the dynamic response to the static response. Okay, and in a minute when we draw some graphs, you'll see why that's a logical choice. But the other reason that people like to use this format is that on the right-hand side, this is all non-dimensional now, isn't it? Because we've got the ratio of two displacements, and on the right-hand side, the only parameter is r, which is the ratio of two frequencies. So everything has become non-dimensional, and that's another reason why people like to use this format. So In the printed lecture notes, you'll find that there's some diagrams showing what's going on here, and I want to pick up on some of those now to just show you the kind of behavior of this system. So you'll find in the lecture notes that there's a diagram which shows something like this. So this is a plot of R against x over x static. Okay? And what we get is something like this. Okay, so what it says is that when R equals 1, x over x static goes to infinity, doesn't it? Okay? Well, even if it's close to 1, you can see that we start to divide by 0, don't we? So this thing goes to infinity. When R is less than 1, okay, so we're on the left-hand side of the diagram. We're in this zone here between 0 and 1. So in that case, the forcing frequency omega is less than the natural frequency, omega n. So we call that low frequency. And that corresponds to the case where e to the minus j phi is equal to plus 1. So that means phi equals 0. Okay, so I'm going to move that up now so we can see, hopefully. Try and keep the diagram there. And then the other case is when R is greater than 1. So that's when omega is greater than the natural frequency. So forcing frequency higher than the natural frequency. So we call that the high frequency range. And then for this case, e to the minus j phi is equal to minus 1. So phi is equal to 180. Okay, and the reason, if you look at the formula, the plus and minus 1 make the signs correct on the left and the right-hand side. So if we look back at this formula, if R is greater than 1, then this right-hand side becomes negative, okay, and then that corresponds to the phi value making the x negative, okay, and in the case when R is less than 1, this right-hand side is positive, and again, so here we get plus 1 from the phase, okay, which makes the left-hand side positive. And you can see where you plot that, you get positive on this, for this case, for lower than R equals 1, and then for this case you get negative. Again, if you look in the printed notes, what you'll find is that there's some plots of the magnitude and the phase, okay, so if you take the magnitude rather than the real parts, we get something like this. Okay, so this is R equals 1 here. This is R, and this is like the, if you like, the modulus or the magnitude of x over x static. Okay, so we get something like this, and then if we take the phase. Okay, so the phase we know has got just two values, hasn't it? It's got 0 or 180. So what happens is that the phase just goes along at 0 until it gets to R equals 1, and then it jumps up to 180 and goes like that. So, sorry, here we go. So for those of you who've done control engineering, these things will start to look similar to Bode plots. Okay, so like the phase and magnitude type plots that you do in control. Okay, so there's obviously a link between this type of representation and say an open loop control system. Okay, looking at the phase and magnitude. So that's kind of all well and good, but one of the major problems is that this system is not really physical, is it? As you noticed, it went to infinity at r equals 1. And the problem is that we're putting energy in through this forcing function f of t, but we're not taking any energy out. So that means when we're close to the natural frequency, it can become unbounded, right? It goes to infinity. So in reality, of course, there's nearly always some damping being taken out or some energy being taken out through these damping elements. So what we're going to do now is we'll go back, do the same derivation, but we're going to put a damping element in, and you'll see how then instead of going to infinity, we get something which is bounded, and that's much more representative of most physical systems. So this part is, we can call this damped force vibration. And as I say, we're going to go through the same type of derivation, but we're going to add a damping element to the system, okay? So we're going to start just where we did before with a mass, spring, and f of t. Okay? But again, exactly like we did for the undamped cases, we now add a damping element. Sorry, we did for the unforced cases. So we're going to add this damper value C. And again, remember what I said in the unforced cases, I said this thing was like a dashpot with liquid inside it. So you imagine that this thing is something like a plunger going backwards and forwards inside a tube of liquid, which is proportional to the velocity of the mass. Okay, so same approach to our derivation. So we're going to take free body diagram first. And this time with the free body diagram we get the same as last time but with one extra force on it. Okay, so we have the inertia force mx double dot, we have the spring restoring force kx, and then we have a damper force Cx dot, which is also trying to resist the motion as you're trying to pull this thing upwards. So we can write down the write down the equation of motion. So hopefully you start to see a pattern emerging from these equations of motion that we keep developing. So this again is the same equation that we had for the unforced case. Okay, remember we had exactly the same terms, but on the right hand side we had a 0 when it was unforced. Now we've got forcing, so we now have some forcing function there. We're going to take the same approach of substituting for harmonic force and response. Okay, so if we do that, what we get is minus omega squared m plus j omega c plus k. That's all multiplied by xa e to the j omega t minus phi. And on the right hand side, we had the same as last time, f equals e to the j omega t. So notice this time that we've got this extra term, the j omega t term comes from the damper term, c times x dot, because we have to differentiate the assumed solution once. Okay, and then we get a j omega t, don't we, which get a j omega, which comes out in front of the coefficient c. So we're going to let x equal xa e to the minus j phi. Okay, and in a minute you'll see that actually this time we're going to allow this function to be a whole range of values, okay, not just 0 and 1, okay, because we can't get away from this being a complex function anymore. Okay, so this is actually, instead of just being 0 and 1, you'll see actually it varies continuously between the two values. But if we do this trick, then we can divide out the e to the j omega t terms, and what we get is, so we can say then x over f is equal to 1 over k minus omega squared m plus j omega c. So same as last time, except we've got this extra term, the j omega c term. Okay, so we want to do exactly the same thing by writing this in terms of x over x static, which remember was x k over f. So what we get this time is you get the same as last time, 1 minus r squared, but now we get a plus j 2 zeta r term on the right, which is our term associated with damping. So how do we get this term here? So what we do is, if you remember, we're taking k out of all of these terms. Okay, so we end up with something like this. We end up with j omega c over k. Okay, so if you remember from before, the damping ratio zeta was defined as c over c critical, wasn't it? That's what we defined in the previous lectures, which is equal to c over 2m omega n. So that means that c is equal to 2 zeta m omega n. Okay, so this is just rearranging this relationship here between zeta and here. So this thing here, the j omega, we can replace that c now with 2 zeta m omega n. Okay. And then we've got an m over k here, which is effectively omega n squared, or 1 over omega n squared, isn't it? So we end up with 2 zeta omega n over omega n squared. Okay, so then that becomes 2 zeta r. Okay, because this goes and this goes, and we get the ratio of omega divided by omega n. So again, this equation here represents the magnification factor, but now it's got this complex part to it. People tend to not use this form. Okay, we tend to go to the magnitude and phase form. Okay, because it's got a complex part. But if you notice what it's got now is just two parameters on the right hand side. It's got the same parameter we had last time, r, which is the ratio of the frequencies, and then it's got this other parameter, zeta, which we know from our previous lectures is the damping ratio. Okay, so we've actually just got two things, and again, they're non-dimensional. Okay, so because this is a complex function, because we've got a plus jb, the magnitude is the square root of a squared plus b squared, isn't it? And the phase is the arctan of b over a. So what we're going to do is we're going to take the magnitude of x over x static, which is the same as taking the magnitude of xk over f, and that equals 1 over the square root of 1 minus r squared squared plus 2 zeta r squared. So we tend to call this one the dynamic magnification factor. Okay, so that's for the damped case, we tend to refer to this expression as the dynamic magnification factor. Sometimes you hear it called the dynamic amplification factor. So sometimes it's called amplification. Okay, so the same. It's just another word for this, another term for the same thing. So let's try and have a look at what this looks like in terms of the graph. So again, in the lecture slide pack, there's some diagrams. So if we draw the magnitude of x over x static in this direction, and r in this direction, what do we get? Well, it should start at 1 on the left-hand side, shouldn't it? Because we defined x static to be the point here where there's 0 frequency or 0 time. Okay, so we should start at 1, and then we'll go up to a peak, which happens when r equals 1, or very close to r equals 1. And then it'll come down on the other side. Okay, if we do the same plotting the phase, what happens is something similar to, we get sort of 0 to 180. And what happens is something very similar to last time, except there's a smooth transition now between 0 and 180 instead of being a jump. Okay, so initially it's close to 0, and then we set this smooth transition, goes up like that to 180. And so what does this mean physically? Well, what it means physically is that here, this is showing what we would know as a resonance in a physical system, isn't it? Okay, so this kind of increase in amplitude is often called a resonant peak or resonance peak. Okay, and the sort of amount that this can be magnified, so from this value here to this peak, can be 10 or 12 times. Typically, right? So it can be 10 or 12 times, can be more actually if the damping is very, very small. But it's very typical to have a magnification or an amplification of 10 or 12. So you can see why engineers become worried about vibrations, okay? Because everything you learn in sort of statics, so everything about stress and strain and what you might call static analysis applies to this case here, okay? So if you're designing your aircraft and all the structural design, you're designing everything to be here, okay? So as soon as you add vibrations and you come to a resonant frequency, you have the potential to amplify all of the loads by an order of magnitude at least. Okay? So that's why you need to be very cautious. If your system, like an aircraft, and many other systems have the same kind of thing, spend all of its operational life in a dynamic environment, then it's continually subjected to sort of vibrations, isn't it? So this is one reason why you need to be concerned about it. The transition in phase, again, we can observe this physically, so we can observe that for low frequencies we get this kind of phase effect between the forcing signal and the input signal, sorry, the response signal, and then we get this transition at resonance going to 180. So this matches our physical observations very closely.